So a recurrence relation is a definition of a sequence such that you're given a number of terms and then you are given the next term in terms of previous terms. So in this example here, this is what's called a first order recurrence relation because you are only given one term of the sequence and you are given the next term in terms of the previous term. Okay, as a function of the previous term. So I'll look at some examples of that in a minute. A second order recurrence relation, you would be given two terms, usually first and second term. And then the next term of the sequence is defined as a function of the previous two terms. And again, we'll have a look at an example of that in a minute. You could, of course, take it further, given three terms, and then the next term in terms of the previous three terms, that would be a third order, etc., etc. But you wouldn't need those for this course. But the theory continues. Let's have a look at a couple of examples then. So here we have an example of a first order recurrence relation, and it's first order because you're only given one of the terms, and you are given the next term of the sequence in terms of the previous term, single term. So if A1 is 1, A2, that's going to occur when K is 1. So when K is 1, we get A2 is equal to 4A1. So A2 equals 4A1, which equals 4, because A1 is 1. We're told that in the question. A3 is 4A2, so that's going to be 16. And we can see that we can see from the recurrence relation that the next term of the sequence is 4 times the previous one. So you're going to get the sequence 1, 4, 16, 64, 256, 1024. And it would continue in that manner, times them by 4 each time. Another example. Again, it's a first order recurrence relation because we are given one of the terms and the next term of the sequence is defined in terms of the previous term. And I put this one in because, as we can see, the previous term appears twice in this recurrence relation, and that's fine, that's not a problem. The fact is it only goes back one term, so therefore it's a first order. So bk plus 1 is equal to bk over bk plus 1. So b2, well, that's going to equal 2 over 2 plus 1, so that's 2/3. Okay, so the second term of the sequence is 2/3. The third term of the sequence, well, that's going to be 2/3, which is the previous term, divided by 2/3 plus 1. Well, 2/3 plus 1 is 5/3. 2/3 divided by 5/3 is 2/5. B4 comes out to be 2/7. And B5 comes out to be 2/9. And the pattern continues. Okay. In some cases, it might be possible to actually calculate the general kth term directly. And you might be asked to do that. So in this case, it's nice and easy to say that bk is probably going to be 2 over 2k minus 1. Okay, that formula will work for all of these four. Okay, 2 is on top of the fraction each time. And we can see that the denominator of the fraction is going up by 2 each time. My final example is a second order example, and this is one of the most famous second order recurrence relations, which hopefully you'll see why in a minute. So U1 is 1, U2 is also 1, and we are given two pieces of information because it's a second order recurrence relation. And UK plus 1 is going to be equal to UK plus UK minus 1. So it's now defined in terms of two terms back, not just one term back. That's what makes it second order. So U2 is already defined, so if I plug in K as 2, I'll get that U3 is equal to U2 plus U1. So that is going to be 1 plus 1, which is 2. And in fact, the next term of the sequence is the sum of the previous two terms. So we've got the first two terms as 1 and 1, the third term is 2, and the next term is the sum of the previous two. So 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, and so on. And this is obviously, hopefully you recognise it, is the Fibonacci sequence. Okay, Fibonacci. Okay, and that is a definition of the Fibonacci sequence. Thank you for watching.